So, good morning all, and a special welcome to our guests in the stream. It's my pleasure to introduce our speakers for the next talk, starting with Karsten Litschel. As a project manager and technical lead of the Mext project at the University of the Bundeswehr in Munich, Karsten bridges the worlds of science, technology, and strategy. He coordinates 13 interdisciplinary research teams and aiming their work towards a common vision. His focus is on international collaboration and sustainable prototyping strategies for medical devices, so ensuring that innovations like neuromodulation stimulators remain adaptable to future technological changes. Joining him is Constantin Mensendiek from TNG, who applies machine learning to analyze time series of biometrical data collected through the Mext platform. Before TNG, he studied computer science in Aachen with a focus on software architecture. The talk will explore how Mext aims to transform depression therapy by making neuromodulation treatments accessible outside clinical settings. Through portable and user-friendly devices, the barriers to apply neuromodulation treatments are allowed significantly and allow for self-directed therapy. The AI-driven analysis of real-time biometric data helps ensure safety and may also allow for potential adjustments to treatment protocols. And this combination of mobile health technology and intelligent data processing represents a practical step towards personalized and scalable mental health care. So, Karsten and Constantin, we are all looking forward to your talk.
Yeah, thank you, Mara, for the nice introduction, and thanks to TNG and Constantin for having me and for supporting me. Yeah, as you heard, my name is Karsten, and this is Deeptech for depression. Our project Mext is funded by Deeptech, and we are based at the University of the German Armed Forces in Munich. And they opened many, many doors for us because we were able to build up, as Myra already said, a project size of 50 people working on 13 different sites on mostly one topic. And this topic is transcranial magnetic stimulation, or short TMS. It's basically a way how to communicate with your brain without opening the skull, which is pretty comfortable, I think. And how it works, you place a magnetic coil on top of your head. You have a rapidly changing magnetic field that translates into an electric field in your brain. So through tiny electric currents, you can modulate brain activity. And if you repeat it, which we do in depression therapy, for example, you can actually remodel neuronal structures. And that is mostly what we're working on, depression therapy. We wanted to make it mobile. And it's not just theory, it's already recognized. So it's happening, and we're just trying to help people when medication fails, because this happens here and there, or more often than we want to. Speaking of medication, super simplified, we have the messenger pathway that is taken by the medication. You have two neurons, and in this gap basically is where the communication happens. Some medications focus on neurotransmitters staying longer in the gap, for example, serotonin. It's like turning up the volume of the brain's internal communication system. Our pathway is basically just zapping the brain, and we are working on the electrons with electricity itself without even touching them. And the cool part is both ways can enhance mood and help with brain health. They just speak different languages. And chemistry on the one hand, or on one side, and electricity on the other side. Our vision and our goal is both mobile depression therapy. Why vision and goal? Vision, on the one hand, we thought like, hey, let's just put this from the clinic into the living room, which is hilariously difficult because there are so many regulations in place. We're still aiming for that vision, but the goal is also mobile depression therapy. We want to build a small device where you don't need dedicated rooms for in clinics, for example. You can put it onto a chair or stick it to a chair or whatever you want to do with it. As you see on the left side, you have a huge device. This is how it has been carried out for the past 40 years. You have a huge device, you have a huge and heavy coil, which we exaggerate a little bit, which is usually held by a mechanical arm. And we're just praying that during the process, the patient is not moving. Because, of course, if you're moving, the magnetic field has a problem with too much air distance. So this is where we're at right now. What we are doing, we want to make it mobile. Our stimulator here in the middle picture, you can carry it with one hand. It's less than 10 kilograms, and it would be already portable. The most exciting part about it is a typical stimulator shoots with sinusoidal waveforms. And we are not sure if there are better waveforms out there. So we rethought the whole process and built up a modular system where we can map any pulse shape that we want that might be interesting for different conditions that are right now being researched or might be researched in the future. In combination with the headgear, might make it maybe more reproducible, that the head can't move anymore. And yeah, this is what we're aiming for right now. To be fair, 2025, it's gonna be close. We're almost there, but we aim for a PlayStation-sized simulator, which is now in development. But this one is only as the classic ones, like sinusoidal pulse shape, just super small, super cheap, that also psychotherapists on the countryside can afford it and can work with it. Yeah, and that's attached to our headgear where stimulation basically can happen. This little box, we've been through a lot over the past 4 years. We were always talking about, hey, we're doing mobile depression therapy. Our first prototype was as tall as me, put on a rack. So we were like thinking about, is this really working? Can we do it? And I think the change came when one of our developers had the idea how he can, through smart software, let's put it like this, save up to 90% of the capacity. Less capacity means fewer capacitors. That means less money, less weight, and of course less parts that we can burn. And since we are burning constantly, at some point we want to stop with that. The pulse shapes are also interesting from two different points of view. If we can modulate or map any pulse shape, that can help in the neuro direction, because different pulse shapes might help us to activate different groups of neurons, or some neural groups faster, without less energy, not as much energy as on the one direction. And we can tackle it from the engineering part, where we say, like, can we come up with a pulse that is as effective as the sinusoidal pulse shape, but just we know that it takes way less energy to create it. And this is what we're also thinking about. If I'm just coming back for a second, we thought this one in the middle that can do everything would be the product we want to bring to the market. After a while, thinking through the business case, like, this is way too much. Nobody needs that. We just need the sinusoidal one, but super small, super cheap, super accessible for everybody. And this is what we want to work on. We want to work on new pulse shapes where we find out, like, oh, I don't know, a rectangle, a triangle, whatever works best, and then develop an easy device around this one pulse shape. And this brings me to the point, first to market. We're not gonna go to market with this high power stimulator that is flexible, probably, because it is probably too much. We are not sure yet, because switching technology develops so fast that if we find the right switches that are cheap and do exactly what we want to do, then it might help. But at the moment, we're thinking it makes more sense probably the other way around. One of the most challenging and the coolest parts about the project is that so many disciplines work together. We have sports sciences, psychology, design, medicine, power electronics, physics, more general way. The difficult part about it is, of course, if you come up with a study design, if you come up with a prototyping idea, if you come up with a concept, you always have to make your point in front of everybody, and that can take ages. But it's also what brought us to the point where we are right now. And I think also how it should be. When we talk about brain stimulation, usually the first thing that comes up is it safe? Yes, it is. But there is a risk, in our case, a tiny risk. There is the risk that seizures might occur. For example, in 0.3 of 10,000 treatments, seizures might occur. And even though it's a tiny risk, our vision is again to bring it to the living room of people. So we need to think of a concept how we can make sure that nothing's going to happen after that, or nothing bad is going to happen after that. So that's why I'm basically here, because this is where TNG comes into place. We're using chest straps and smartwatches to track in real time vital data signs to see if any major events occur during therapy session, that we can immediately turn it off and automatically call for help. This is what we basically want to do. The safety is number one. The exciting part about this again is we're thinking, since a lot of products out there are trying to track or trying to define the emotional state of a person via vital data tracking, we can maybe also optimize the therapy, because in the end we will end up with a lot of data that we can correlate to patients that had treatment with the same vital data signs at that moment, that the app maybe just says, now is not the right time. I'm not ready for this therapy right now, so the app just blocks the protocol that would be suitable for you today and sends a notification to the clinician who works with the information. Okay, why is it not today? Is it working tomorrow? Are we losing a day? Should we refine the therapy? So we're going from safe therapy to smart therapy. Not yet, but we're trying. And this is basically a short overview of what we're doing. We're trying to measure for us the most important parameters: ECG, electrodermal activity, temperature, movement, things that are being highly researched when it comes to epileptic seizures. Epileptic seizures is a huge area, which we're lucky that we just have to cover a small part of that, the seizure type that is happening. Otherwise, we could not make it. But this is where the vital data tracking system comes basically into place and should abort the session if necessary. But I don't want to give too much away. Constantin is going to talk about this in detail. We didn't have a chance to talk about the headgear. Compared to the stimulator, it's not. It doesn't look like as much as it is. It is basically 3D printed parts, a few pads, and we wind the coil ourselves. And that's what it looks like. And actually, funny story, we had a visitor from the Technical University of Munich who was, we were working together, and he was looking at the project and saw our developer showed him the headgear, and he was, okay, this is interesting. So this is the low-tech part of your project? And I was just looking at my developer, and I could see the soul leaving his body, because that, of course, hurts when you hear something like that. And yes, it is. It looks low-techy, but it's precision at heart. It needs to be finely adjustable. It needs to be so highly accurate while we stimulate, because we really need the perfect spot with the X marked here. Because if we miss that spot, it means we need more energy in our system, which means the system needs to be bigger. So the more precise we are, the smaller the system gets, the cheaper the system gets, the more accessible it is. So all in all, it looks easy, but it is a pretty cool development. And you also have to think about the coil that is put into the helmet. It weighs around 800 to 900 grams, more or less. Neck stiffness is correlating sometimes with depression. So the last thing that you want is that people sit here and their head is falling to the front, more or less. I had the honors to manage this project for 4 years now, and I wanted to build it up in the idea of a little bit of an industrial project, maybe, if you want to call it like that. We didn't want to do just one thing. We wanted to see, like, hey, if we have this vision and if we're selling it, we should also think how we can make it happen. And this takes a lot, because the vision, everybody was like, yeah, sure. And it is insane, but we're trying to ask the right questions. Maybe partners or people that we're talking to might answer them for us in the end, or together. We have the prototype in the center of everything. And it's, of course, not just about depression. What we knew early on, it was just the start. And when we grew, we also discovered human performance modification, or better known maybe as neuroenhancement, is pretty cool and can be a lot of fun. And that is also what we're doing. And early studies suggest interesting things about enhancing focus, motor control, visual detection. More to that in a bit. We built up a regulatory backbone. That the worst part about a medical device, of course, is the certification. Quality people would say, like, hey, that's the most interesting one. Yes, it is, of course. And but we need to come up with a task force that basically helps us to really maneuver our way through the jungle, that we can, first of all, do studies, because the EU regulations are pretty strict on that, and that we can bridge the gap between lab and clinic in the end. And to close the loop, we have our wearable system that tracks vital data, where we can assure safety and maybe in the future optimize our therapy. And this is, the summary of our project, what we're doing. But let's dive into it a little bit. Our stimulator here on the left, what is actually happening before or during a therapy session. The coil is already placed on the head, and this picture just in motor cortex. And I'll just play the video. Wow. 4 years, a few millions, hours and hours of working to see that. For us, it looks simple, but for us, it's actually a lot. It's way more than that. It means exactly what people told us in the beginning. You can never put this much energy and this much power into such a small device. Everybody told us that, and we were like, 4 years ago, I would say, like, yes, I think so too. Now we're like, hey, cool, it worked. So this is a motor-evoked potential. It is, for us, the best way to see. It's basically creating an action potential with our stimulator. It shows us that our stimulator has the power that it needs to create exactly what we want in the end. And this was a long run, but it's precise enough and it's powerful enough. So a good first step. What's getting more and more interesting in nutrition and pharmaceuticals, wherever it is, medical treatment as well, is personalization. And we have 2 cobot systems that help us to basically be precise as possible. Here we're not talking about, hey, this is a cheap everyday solution for everybody. This is, just fancy, cool research stuff that we're doing. Just going to show you real quickly what's happening. Before the treatment, you get a brain scan. Your brain scan that we have the 3D vision or the 3D idea. After we have your brain scan, we feed it to the software, to the neuronavigation software, which now can work together with the EEG with the brain activity measurements and the robotic arm. So the robotic arm basically has every information that it needs to maneuver to the hotspot, to the spot where that we want to have, that the finger twitches as strong as possible, that we can learn and learn and learn and always need less energy. I think there's something missing, but... There it is. Yeah. So we just want to use this system to have surgical accuracy while placing the coil without using surgery. Is an interesting feature, but of course not for the masses, not for everyday clinics. The fun part now, human performance modification, neuro enhancement. We are now using electrical stimulation. And one scenario is a shooting range scenario where you can apply electrical stimulation before performing the task. You're trying to aim at the regions that are most interesting for the task. She's good, by the way. And yeah, we try to aim for the regions with electrical stimulation to enhance focus, to enhance reaction time, reaction speed, to see what's going on. First studies are out. It is interesting so far, but there are more ways to go. We do pilot training, pilot studies, same principle. The most difficult part and the most criticism that neuro enhancement gets, and I understand why, study design is a huge topic. Study design, meaning if we were, I hope no pilot is in the audience, if we were starting landing approaches, which are super difficult, we would get better and better and better. If now I stimulate you before training, we could not see if really the stimulation was doing their thing or not, which is clearly. So we need people to plateau at something where they're not getting better by the time they're doing it. And this is the most challenging part, actually, and where the studies right now are getting the most criticism from, I think. And of course, sports or working out, lifting doesn't have to start in the gym, but in the brain. We can shoot a few neural warm-up pulses. That's what a few scientists of us doing right now. That just coordination and muscle response works better altogether. As you can imagine, always the analytics are super difficult, so it's really hard to see if really the stimulation did what we thought we saw, but that's what we're working on, because it's just a promising thing that we can lift smarter in the future. And last but not the least, it's not only about safety when the product is out there and when it's already with the people. We also want to make sure that we avoid animal studies if possible. You can gain preclinical data by using the right neuronal models. It's also really difficult because you have so many different types of cells, so many different types of modeling. But that's what we are doing at the Charité in Berlin. We're zapping different kinds of neurons, of cells, basically to ask the cells first, are you okay with that, before we move on to the patients. Yeah, that's it from me. Here you go.
So I will present the next part, and in this part we will dive a bit deeper into time series analysis. So right now you've heard a lot about all the different disciplines and all the different parts of the projects that are involved, and now I want to tell you what the time series analysis part is about. And for that I've brought you two examples that I've worked on in the last year. And the first example is the MAP classification. So MAP is the motor evoked potential, so what we've seen in the video. And then the second part is about the epileptic seizure detection. And the seizure detection is a way more involved, more complicated, way more challenging task. And that's why I'm first doing the MAP classification to get you all up to speed. And this is the signal that we are capturing during the map experiments. So what you've seen is that the patient, so we stimulate the motor cortex, and then we get this response at the finger. And you also saw that there are 2 electrodes placed on the finger, and the difference in potential is an EMG signal, and that's what we can see here. And I've brought you 3 different examples. So in this example, here we see a very strong response, and so we also see a very characteristic waveform. So it's called a biphasic waveform because it first goes up and then it goes down. And then in the second example, right here, you see only this very small bump because of the scale, but that's also probably a map. And then in the last example, we can't really see anything, and we can't really be sure if that's only baseline. So let's zoom in. And now we can see in the middle example that there really is this biphasic waveform going up, going down, and back to the baseline. But in the last example, it's like really hard. Is it just baseline noise, or is there a map? So we probably want to classify this as there's no map. And that's exactly the task. What we are trying to do here is simply to differentiate between signals that have a map response and signals that do not. And why we are interested in that is because in the next step, we are calculating the latencies and the amplitude of the response. And we can only do this properly if we know if there is a map or not. And yeah, for example, here we have like latencies of a bit more than 20 milliseconds, and that's also just the time it needs to travel, the signal needs to travel from the brain to the arm. And so we expect that the signal only occurs after 20 milliseconds, but it can still be different for each patient, and also like in the course of an experiment, it can also change. So we evaluate this to see differences interpatient and intrapatient. And what we need for the classification is a time series classifier. And the basic understanding is that we input a signal. In this case, it's an EMG signal. Then we have some kind of model, and this model is then able to tell us there is a map or there is no map. But then, of course, there are many different possibilities to implement, to train such a model. And so we need some kind of metric in order to evaluate which models are better than others. And this is like a pretty standard classification task. So what we are usually are looking at are so-called confusion matrices. And here we only have 4 cases because we have 2 labels, map and no map, and we have a prediction map or no map. And in combination, we then have these 4 cases. And then we can have a look at certain ratios, which are interesting for us. So one ratio that's interesting is the precision. And the precision calculates how many of the predicted maps really are maps. And then a different ratio is the recall, where we look at how many of the actual maps are also predicted by our model. And then finally, we can also combine these 2 scores into one. And this is often done with the so-called F1 score. And this score uses the harmonic mean of both. And the advantage of having one score now is that we can rank our models and select the best one. And that's exactly what we did. And so we implemented our own models. And the best model we came up with was, in the end, a support vector machine. And a support vector machine doesn't use the raw signal, but instead we need to engineer certain features. And these features are then calculated, and then the training is done on them. And so in this example, I simplified a bit. In fact, we have many features, but here I only reduced it to 2. And right here we have on the y-axis the timing of the maximum of the signal, and then on the x-axis we have how well the signal matches this biphasic waveform. And then all the circles are different signals where we calculated these features for, and the colors indicate whether there is a map or there's no map. And what the support vector machine now simply does, but usually like in a hyperdimension, it finds a line, or more generally a hyperplane, that separates these two classes as good as possible. And by training this model, we were able to get a pretty good score of 95. And we also compared these to other state-of-the-art models. And there we also got a respectable score of around 90%, which is also quite good, but still not as good as our model. So then we were quite happy that our model really is a bit better than other state-of-the-art models. But these state-of-the-art models also have quite a few advantages. In particular, we don't need to engineer features ourselves, but it's like some neural networks that engineer features or learn features by themselves. And so you have to do less manual work in the beginning. So that's the basics of the map classification, and now I want to come to the more interesting and more challenging part, and that's the epileptic seizure detection. And first, a definition. So an epileptic seizure has like a very general definition of just being a sudden burst of abnormal electrical activity in the brain. So, and epileptic seizures are, like Karsten said, they are very diverse, and very many cases are there, and so we categorize these different seizures. And they are mostly categorized by the onset and also by the motor component. Onset means where does the seizure happen, where does it start? And there we have the difference between a seizure that starts at one focal point, one point in the brain, and a generalized seizure that's happening in the whole brain at once. Then the second category is the motor component, and there we have like the extreme case of a tonic-clonic seizure. A tonic-clonic seizure means that the patient is alternatingly stiffening and jerking, so it's like the very extreme case that most people associate with seizures, but there are also other movements possible. And in particular, there's also on the other side of the spectrum, it's also possible that the patient has no motor at all and that he's simply staring into the distance and is not reacting to anything. And here I brought you an example for an epileptic seizure. And what we can see here is that we do not have one single signal anymore, but many different signals. And that starts with the upper signal, the EEG signal. That is a signal of the electrical activity in the brain. Then we have the ECG signal, which records the activity of the heart. And then finally, we have the acceleration data, which captures how much the person is moving. And in this case, we have a focal to bilateral tonic-clonic seizure right here. So that means the seizure starts at a single point, but then it spreads in both halves of the brain. And also with this spread, the patient starts to move in a tonic-clonic way. And each signal looks a bit different. For example, here in the EEG, we can already see in the beginning that the brain activity looks a bit abnormal, and then it grows more abnormal with the time. In the case of the EEG, we don't see such a stark difference in the beginning, but we see that the heart rate is increasing more and more because we see these sharp peaks. These are so-called R peaks, and they are like when the heart is beating. And so if these sharp peaks are getting closer to each other, then the heart beats faster and faster. And then finally, the acceleration, there we see in the beginning, the patient isn't moving much. That's because I think this recording was done during sleep. So the patient is sleeping, and then he suddenly gets a seizure. And then as the seizure spreads in the whole brain, he's also starting to move a lot and erratically. So let's compare the two use cases, so the map classification and the seizure detection. And the input is different. We've seen that now we have a multidimensional signal, and also the recording doesn't have a fixed length anymore. then the labels are now not just binary, like map or no map, but instead we have some event with some time stamps. That's also the reason why we need a different metric, so some kind of event metrics. I will go into more depth later on. And then the application is also fundamentally different, because in the use case of the map classification, we are doing this evaluation offline. This means we are recording all the data, and then after the experiment, after the study, we are doing the analysis. But in the case of the seizure detection, we want to do this online. And online means we are doing it in real time. So let's have a look at all the different challenges in a bit more depth. First, the multidimensionality. There are two basic strategies that can be done. And the first one is the early fusion. In this case, we are trying to combine modalities as early as possible and then train one model on all the fused data. On the other hand, we have late fusion, which means that we are training models on single modalities, single channels, and then in the end combine the results to get one overall detection. And both strategies are valid and have their advantages. In particular, early fusion is important if the data has some correlation, and we need to capture this correlation for the correct detection. Late fusion, on the other hand, has the advantage that we can have one model specialized on a certain modality. And then also if at some point we maybe have a different modality or we are removing a modality, it's pretty easy to do because we can just train a new model or remove the old model. So both have advantages. The next step is how to, what kind of model we are using. And you've already seen the standard time series classifier, but we can't apply it just as it is, because then we would need like a fixed signal and also only like an output of classes. But now we have a recording of variable length, and also we don't want just true or false, but we want an output of where the seizure actually happens. And that can be achieved with a sliding window. So let's have a look. Nope. Actually, that's an animation. Let's see if I can start it.
Vielleicht, wenn du da drüber gehst. Über den Bildschirm, geh nochmal mit der Maus raus.
Du meinst auf der Seite?
Ja, genau.
Ja, das könnte besser sein. Well, it doesn't work. It doesn't matter. I can describe you what would have happened. You can see this sliding window in purple, and that's a time window that slides along the recording. And then for each window, we get one classification. And this is like the first classification here, and then you would have like a graph here that shows like the prediction probability going up and down, which shows how likely the classifier says that there's a seizure. So here is like the result, which would be that we have this annotation where we know that the actual seizure is happening. And then this row right here would be the prediction. And so maybe the model finds it hard to find the exact starting point because in the beginning the seizure isn't as abnormal, not much movement yet, but in the end there's a lot of movement, and also afterwards the heart is still racing, so maybe the prediction is that we start a bit later and it goes a bit longer on. So now we want to evaluate how good this prediction is. And for that, we are looking at different things. The first thing is, again, the sensitivity. And this means we are looking at how many of the actual seizures are also found by our model. And found is not really precise. So what we're doing is we're looking at the overlap. So if the seizure and the prediction overlap, then we are saying that that seizure was found. The problem now is, if we simply predict everything to be a seizure, we would also find all seizures. So we need to balance this out. For that, we have the so-called false alarms that we are measuring. And since we could just do one long prediction, we need to do something a bit different here, and that's what is called epochs. So we are doing an epoch-based method where we are counting, in this case, we have 5-second epochs, and we can see this down here. And so the first epochs are all within the annotation, so they are all correct, but afterwards they are outside of the annotation, and there we have false alarms. And then one more thing that's interesting is the latency, because we want to do it in real time. And that's also like one more challenge, the real-time analysis. There we need to have a look that the model is really compatible with streamed data, and also that it can be executed really fast. Because if a model needs 10 seconds to execute, then maybe it's already too late. And then one last challenge that I haven't really talked about yet is just data availability. In order to train a good model, we need good data and we need a lot of data. And in particular, also with the devices that we want to use, we don't really have that data yet. But we want a smartwatch and a chest band, and we want recordings of epileptic seizure patients. But that's quite difficult because seizures are also happening not really often. So that's what we are just currently doing, and that is doing a study with the LMU, and there we are collecting wearable data, and we hope that we can get a lot of good data there and then apply all the experiences that we've already collected with epileptic seizure detection. And that's it. So thank you very much for your attention, and we are open to any question, so thank you very much.
Thank you very much, and I see there are already many questions from the audience.
Hi, thank you so much for the talk. I basically have 2 questions. The first is that in the case of treating depression, what is the process of validation that it is working? Like, is it the behavior and you ask the patients for feedback, or are there any quantitative metrics that you can measure that depression treatment is actually working? And the second question would be in how strong is the magnet? Does it interfere with the EEG measurements and the portable devices?
Good questions. Since I'm only project management, I can't go too deep in every question, but let's start with the second one because I think it's easier for me. Yes, it does interfere with the EEG, and I think there's also a huge artifact, but I think our people have designed more or less a way to measure or like calculate with the artifact and still see everything what they want or what they need. Is that correct?
Yeah, so it's the people in Regensburg that are doing that, and we have seen this video with the robot arm, and there they had this EEG helmet on. And in that case, when the stimulation is triggered, we have like a really huge artifact. But the good thing is, if you properly set everything up, then this artifact is really short, and we can kind of just cut out this artifact, and then we can still see the reaction of the brain in the data.
And for the first question, everybody, please correct me if I'm wrong. As far as I know, when it comes to psychotherapy or how a patient is doing, you have 2 scores, one from the patient and one from an observer, how it's changing, how the therapy is working. And what we're doing with EEG, you have basically what I was talking about, like when we compared human performance modification with depression therapy. The idea behind it is if we can make an underactive brain more active, which we're trying to do by depression therapy and which is measured via EEG, the specifics I don't know, we can also make a healthy brain perform better through human performance modification. So yes, I think there is some ways you can measure, but I'm not 100% sure how the waves are changing in the EEG measurement.
Thank you a lot. I have really contrast feelings after your talk. I am explain it. So I'm originally from Ukraine and cannot think out of war scope. And you mentioned that you can influence serotonin. So like more serotonin, it's good for depression treatment, but less serotonin leads to aggression. You also say that you can influence muscle power, reaction, and so on. And for me, it looks like you found the way to create a perfect killer. Do you see, like for me, it's a danger a bit, because you said also that you would like to have this device cheap and affordable, private.
That's a good question. That's one that I'm asking myself also when we're doing these things. So we are not 100% affecting serotonin as a medication does. That was the medication pathway. So for us, it's, I think, a little bit harder to measure. So it's not super directly this pathway as the medication is going, because I think pharmacology-wise, you can map it out really clearly. But yes, what everybody thinks, if you see this, especially when you put it into a helmet, is a super soldier. It is kind of a little bit questionable. The whole neuro enhancement might be questionable. I think it's as with every technology, if you use it right, it can be good for learning enhancement. For example, if you have a astronaut or a surgeon who is concentrated for 1 hour more, it can really help. But of course, you can use it for a lot of bad things. I think, yeah. I mean, my personal opinion is always like, if you can avoid things that might make things difficult, then maybe do it. But I also don't want to hinder the researchers in our team from doing what they want. And I think they're doing it really responsibly in a way that is supervised, in a way where you can say, like, let's keep it in a reasonable manner, yeah.
And also, like, the enhancement is only, like, really slight. It's like improving the focus a little bit, maybe the memory is a little bit better, so it's not like we're at a point where we are creating, like, superhumans or anything.
For now.
Like change it, and do you have some experiments or in the way how it could negatively be developed?
I think that's a good question for the future, and this might also be a point where in the future, if you have exactly these higher effects where you can see like, whoa, now we're going exactly into the direction you're talking about, then I think you need to ethically rediscuss everything about that topic. I think now it's interesting science because the effect is so slightly, like if you have a coffee, you might be better than with our stimulation probably. But yeah, I'm 100% with you. This could be in the future an issue and should be rediscussed probably.
Hi, thanks a lot for the interesting talk. I have 2 questions as well, one for each of you. The first one, it's a bit related to what we've heard before. So I know that in depression treatment, it's a very individual thing, and there's a lot of medication, and different patients, like different medication works for different patients, and for others it doesn't. And there's a lot of research there, and I'm sure there's a lot of data. But then for your application, I was wondering, do you have any data on that? Like, does your method work for the same patients that would respond well to medication, and for others it doesn't? Is there a correlation between that? Does it work for everyone, for anyone? Does it work better than the medication treatment or worse? Do you have any data on that?
Yeah.
That's the first question. And the second question is about the seizures. You were talking about only the AI part of how to see the seizures from the data. And the very simple question is just, how do you verify it? Like, what is the indicators for seizures that is not from the data? How do you say if the AI prediction is correct, basically?
You start.
Okay. Yes, so since I don't know for how long the treatment's been going on. I think for 15 years, more or less. So you have a lot of data that it works. I think in around 60% of the cases. And I think it's comparable to medication, from what I know. It's difficult with the studies. Like, of course, you have non-responders. That was also one of your question. You have non-responders. What I saw when I am going through the studies, which I unfortunately do not do that much, you see that a few people taking medication also getting TMS treatment and getting better through this, but a lot of them are also having nothing because they're non-responders to medication. In Germany, for example, you only can go through TMS procedure if you're a non-responder, and I think to 2 medication treatments, and after that you can basically TMS can be applied. So yes, you have data, it's comparable. Side effect wise, we have lower side effects, but this one that like kind of hits you in the face when you see it, like, whoa, there's seizures happening. Yes, but this is what we're trying to make better. We're also working, I don't know if it's of interest, but the placebo is of course always a big question. What's happening right now to make the procedure even better? You have always a placebo effect, especially when you're sitting in a fancy chair with a robot around you. And we're developing a coil right now where you can influence the magnetic field in 3 dimensions. Because right now the placebo treatment is basically happening. You just use a different protocol where we think, or we're pretty sure through measurements that it doesn't do what we want to do, but you still have a stimulation going on. And we're trying to just cut the magnetic field completely out, that it doesn't even go into your brain. And this would increase basically the data also and make the whole therapy better, I think. Was that okay, or are there sub-questions left?
No, thank you.
Okay.
Okay, then to the second question. It is really hard to identify in wearable data whether or not there is a seizure. But in EEG data, it's simpler. So what we're doing in our study is that in the LMU, they are already recording EEG. And then in addition, we also have the wearable devices. And then we have an expert looking at the EEG data. And then he can correctly annotate where the seizure happens. And then we can look at the same time frame on the wearable data, and then we know that the seizure happened, and then we can look if there are any changes in the heart rate or anything so that we can predict it, so learn to predict it.
So we are already out of the time box, and due to the interesting talk, thank you again. There are a lot of questions. Maybe if there are very urgent questions, you can steal some minutes of the coffee break of the time of the speakers. And for all others, we have now a coffee break of about half an hour. So feel free to grab snacks and a coffee.
Thank you.